on Lesson 40, Unit 7-4, page 448, Part 2, double angle and half angle identities. We have these identities. We've got the sine of 2a formula, the cosine of 2a formula, the tangent of 2a formula, sine of a divided by 2, cosine a divided by 2, and tangent of a divided by 2. Okay, the interesting thing is to be, if we don't memorize these, then it's hard to think up what things are going to zap into. In other words, if you look over here at number 11 and you see the top is cosine 2a, if you don't have in your mind what that expands into, then what you're going to do for this problem isn't readily going to jump in your head. Even if it didn't, though, in this particular problem, it's interesting what we see, even if we don't look at the numerator there. If we look at the denominator here, and we look at what's on the left side, what do you notice about those two items? They're really binomial conjugates. We could look at the sine A plus cosine A on the bottom right as being cosine A plus sine A, which would make it the binomial conjugate of that. Now, what do binomial conjugates create? Well, let's talk about that. If I had A minus B times A plus B, what would the result be? The difference between the two items squared. Now, if the numerator would zap into the difference between the two squares of those binomial conjugates, this would be an easy job to fix, which it does. And so hopefully that you would recognize that. There's a lot of math that's just going to jump out at you, we hope. It's got to be in there to jump out at you. And so what we would be thinking then is there a possibility that the cosine of 2a would result in the binomial conjugates, or the difference between two squares of the two yellow binomial conjugates, and in reality it does. We have some options of how to expand cosine 2a, and we would prefer to expand it as the difference between two squares because that makes it an easy factoring job. So we're going to replace then the cosine 2a, I hit the wrong button. Let me get that off of there. We're going to replace cosine 2a with cosine square a minus sine square a. And we're going to rewrite the denominator in a different order using the commutative property of addition, cosine a plus sine a. We know that the new numerator, cosine square a minus sine square a, must have come from the binomial conjugates cosine a plus sine a, cosine a minus sine a. So we changed cosine 2a into the difference between the two squares, cosine square a minus sine square a. We realize that that will factor into the binomial conjugates cosine a plus sine a, cosine a minus sine a. And on bottom, we could actually group that in a parenthesis, cosine a plus sine a. And then what we have, obviously, is a simple cancellation of a factor in the numerator and denominator, which leaves us with our desired result, cosine a minus sine a. That's our target, and so we've verified that number 11 indeed was an identity. Any questions on number 11? This is not necessarily easy because there's a lot of memory work to do, but there's also a ton of algebra that just to jump back in your mind randomly at any given point. And for that to happen, it's got to be in there, but not only in there, you've got to understand it enough so that it does start jumping out when you need it. And that's not easy. I remember when I first started doing this, it wasn't all jumping out at me. now that I've got a better grasp of Algebra 1 and I've taught calculus, and calculus stuff just, it has to jump in your head all the time. So I'm kind of used to that, and that's helped me out here with the trig. The trig is supposed to help out with the calculus, but it's been backwards for me because I taught calculus before trig. So that was kind of challenging. But now I'm finally learning all the trig because I've dug it out of the calculus. I'm teaching pre-cal. Any questions on number 11? Okay, number 12 is a little bit of a tricky thing to deal with. So number 12 is tangent A over 2 is equal to sine A over 1 plus cosine A. Now, what we do is we go from the more complex side to the least complex side, and the more complex side is the right side. It's obvious that the result is going to be a half angle something. So there's probably some half angle stuff involved in this, right? But you don't see a half angle. Now, let's talk about something. If I had the sine of 30 degrees, or let's just say the sine of 15 degrees. Excuse me, I'm going backwards here. The sine of 15 degrees could be rewritten as what if we had a half involved? It could be rewritten as the sine of 30 degrees over 2, and then you could apply the half angle identity, okay? What if we had the sine of 1 degree? What would half of that be? It would be the sine of 2 over 2. So sometimes we do little tricky things just to get something to pop out, right? So what if we didn't know what the angle was? What if we said, well, let's just let the angle be 2, but I want to write it as a half angle, so what would I do? I would say sine of 1/2 of 2 times the angle, or the sine of 2a over 2. So sine A is the same as sine 2a over 2. And that writes it as a half angle situation. Okay? So if we're in need of getting a half angle situation, and all we got is A, we have to go 2 times that over 2, and it's equivalent. So we're going to cheat a little bit here, or be sneaky. It's not really cheating, it's smart math. We're going to rewrite this as the sine of 2a over 2 over. Now, cosine A could be done the same way if we wanted to, right? We could think of it as 2a over 2. So we're going to rewrite this also as 1 plus cosine of 2a over 2. Okay, so what we're looking at in our mind is we're thinking I've got tangent A over 2. And I know that there's a relationship between sine, cosine, and tangent. That relationship is the fact that sine A over cosine A is equal to tangent A. We know that. Now, if that's true, then we know that sine of A over 2 over cosine of A over 2 would be equal to the tangent of A over 2, right? So we're kind of close to that because we got some sine of something over 2 and some cosine of something over 2, and we're trying to make our way to tangent something over 2. We just got to figure out how to make our way from one end to the other. And so we're going to take a peek at what we've got here. We've got a double angle identity for sine. What does it expand into? A half angle identity for sine, excuse me. Actually, let's not do that yet. We don't like, let's do that, and then no. What we were thinking is if we use a half angle identity, look at the mess we're getting. If we use a half angle identity, look at the mess we're getting. We don't like that. That's not pretty. It's just not pretty at all. So maybe we could avoid that, and instead of calling it a half, call it a double. Doesn't double look prettier than half? Let's maybe see if we could do that. Okay? So here's what we're going to do. We're going to rethink this. Instead of having 2a over 2 and thinking of it as a half angle identity, we're going to think of it as the sine of 2 of those halves. Now it's a double angle, not a half angle. It's 2 halves instead of a half of 2 wholes, half of a whole. Okay? So now we're thinking of it as a double situation instead of a half situation. It's the same thing. And so we're going to think of this as 2 of those somethings. So instead of having half of something, we now have 2 of something. Same thing. And so we're going to avoid those ugly half angle identities, and we're going to use these double angle identities and still hope that somehow it'll get us over here to the tangent situation. Okay? What we're going to do is right here, we're going to replace sine 2a with this situation. But my question is, what is my a? In this, my a is really a over 2. So where it says a, I'm going to put a over 2. Okay? And so we're going to have the sine, or 2, sine of my angle, which is a over 2, cosine of my angle, which is a over 2. So 2, sine of the angle, cosine of the angle, over 1 plus. Now, I've got the second part to replace. I've got cosine of a over, cosine of 2 of those. So the cosine of 2 of something, and I'm going to replace it with this one, 2 cosine square a minus 1. So I'm going to replace that portion with 2 cosine of my a, which was a over 2. It's cosine square. 2 cosine square of my angle, which is a over 2 minus 1. And all of a sudden, my a over 2's jumped back in there. We used a double angle identity. The name of my angle was a divided 2, so I've got my a over 2's back. Now, there's a nice little cancellation on the bottom of a positive 1 and a negative 1 right here. So those go out, which makes it a little cleaner because that's going to make us have all multiplication. I'm just going to bring this up here. We're going to have 2 sine a over 2, 2 sine of a over 2 cosine of a over 2 over 2 cosine square of a over 2. So there's where we're at. Now it's multiplication, division, and we have some cancellation opportunity. The 2 here will cancel the 2. Cosine to the first, cosine to the second. There's one more cosine on bottom than top, so it leaves us with 1 cosine on bottom. So we end up with cosine of that angle a over 2 on bottom, and we have sine of that angle a over 2 on top. Now that was our target because we know that sine a over 2, cosine a over 2 is equivalent to tangent a over 2, and tangent A over 2 is our goal. So that turns into tangent A over 2, and we've verified that it's an identity. Again, some of this can get very complicated. That's a very, very, very complicated problem there. And they range from somewhat simple to very, very challenging. To be able to read into it and think about all the different options. Any questions on lesson 40? All right, yes, sir. Yes. Uh, the the tangent A over 2, yes. And this tangent A over 2 is equal to sine A over 1 plus cosine A. Um, is that form of that identity right there. Obviously, if that was the case, you could make a direct substitution and do it in one step. But what we just did is proved that identity with other identities. Yeah, on the test, we wouldn't want to have an identity on the test to prove. But that shows you how complicated proving the original identities can be. Any questions on that? Also, don't forget that if we had situations that caused a division by zero error, we would have to cast those situations out. And there's times where you would need to make a disclaimer that 1 plus cosine A could not be equal to 0 or whatever. And so you could find the values of A that would make cosine A negative 1, which would create a division by zero error, and we'd cast some of those out. I'm not really going to get into that. We just need to know that that's a reality, that you can't have a division by zero error. So cosine A can't be equal to negative 1. When is cosine negative 1? At 180. So that would exclude from the domain A being 180. So we got to kind of remember that that's going to be going on all the time. Any other questions or thoughts on this?